We finished sorting last time, and we're going to move on toward talking about searching, which is a natural way to fit in stuff about data structures. Now, the way that your curriculum's gone so far, you've kind of picked up bits and pieces about data structures along the way. Here are some of the basic data structures, and Mark's going to talk about these this week during recitation as a review and as an introduction for those of you who either know it well or don't know it at all. You can choose different things. If you don't know it at all and you feel you want to review, then definitely go. But if you feel this stuff is just real basic for you, stacks, queues, and linked lists, and you just know it, then we'll have some other more advanced topics that are optional but alternatives to this. You've all used these, and even these, even trees, in different applications, both in the Scheme course and in the Java course along the way. And because of that, I'm going to leave the discussion of it to recitations and concentrate on algorithms more and only data structures that are really advanced versions of these. So the data structures that we'll end up talking about, which are fancier than these, are three, ones of which you've seen: heaps, and then graphs, and then I'll call them, well, let's call them what they're called, red-black trees. Basically variations of binary trees. This decade, red-black trees are the popular version. A decade ago, they were called AVL trees. Well, different version of that. There were weight balance trees. There's all sorts of different ways of manipulating trees so that they do a little bit more about what we like. And red-black trees, I think, have kind of evolved into the version that most people study nowadays, and we'll get to that later today, probably. So here are the data structures that we'll end up studying, and we'll study algorithms with respect to them. And here are some data structures that I assume you kind of know, and details and implementation and stuff like that can be reviewed in recitation. So that's the big picture. To make a segue between sorting and searching, in which these data structures kind of show up a little bit, we're going to talk about one final problem which is really, really practical, and that is, if you have a big list of numbers, how do you get the middle number, the median number? Or we talked about getting the biggest, the second biggest. We talked about getting the kth biggest. How do you get the middle one? So in your problem set, there's one suggestion for getting the kth biggest, and it basically uses heap sort. Remember when we use heap sort, we sort the array by getting the biggest, and then the next biggest, and then the next biggest, until we get them all in order. And every one of those steps takes how much time? Every step to get the next biggest. Who remembers? You have to take the biggest from the top, you stick it on the bottom, and then you have to fix the heap. And fixing the heap takes log n. So if you did this k times, you could get the kth biggest in k log n. Right now, that's OK, except if you want the middle one, and if you want the second one, that's 2 log n. That's pretty fast. If you want the third one, it's 3 log n. That's still a constant times log n. It's still log n. It's still fast. But if you want the middle one, you're getting n over 2 log n. And that's just order n log n. You might as well sort the thing as far as the constant factor goes. So that's not fast enough. We want to be able to get our median algorithm down to a linear time. And there's definitely a way to do this. And the method that we're going to use is one of a number of different methods. There are some details chosen to kind of make it work out with the constants. But it's really a cool method, and it's been around at least for 25, probably 30 years or more. OK, questions so far? So we're going to talk about a method to calculate the median, or in general, the kth largest number in a list. Median is a special case of that. Now are there questions? All right. Here's a method. The motivation for this method is that it's going to be recursive, and it's going to come up with a recurrence equation that is also really tough to solve explicitly, but which, if you stare at it and guess that it's linear, you can prove that it's linear by induction. So people created this algorithm trying to come up with an idea that would model such a recurrence equation. So the recurrence equation you're trying to hit is what guides you in choosing the algorithm. And now I'll explain the algorithm. You'll see the recurrence equation, and you'll see really where people were coming from when they think about it. So here's the idea. You take your numbers and you put them in a big table, a two-dimensional array that is size 5 by n divided by 5. N is the number of numbers in your list. So you split it up into this table. 1, 2, 3, 4, 5, and then lots and lots of columns. So in each column there's 5 elements. Okay so far? All right, that's not so hard. Next step. We're going to take each column and calculate its middle value, not recursively, just by a separate process that finds the middle value of 5 elements. I'm not going to tell you exactly how to do this, but I will tell you that if you're really careful, you can do that in 6 comparisons. You can find the middle value of 5 elements with 6 comparisons. Now, I once had a student, after I told him this, who went home and came back the next day with I don't know how many pieces of paper, 18 pieces of paper, going through every possible combination of 6 comparisons on 5 elements, and then trying to convince me that none of them identified the median. And since he was so sincere to have spent God knows how many hours doing this, I spent God knows how many hours looking through his 18 pages only to find the one case that actually did work. And anyway, so don't do that, because it really, there really is a way, and you can find it out. And if you don't, and if you can't figure it out yourself, I think Mark's already worked out a way with 6 comparisons. So it can be done if you trust Mark, and I do. And once you find that middle element in each column, you put it here. I'll put a little star there. That's the middle one. And you partition these 5 columns so that the smaller 2 are up here and the bigger 2 are down here. So I'll put little minuses for the smaller 2 and little pluses for the big 2. Okay so far? We'll analyze how much time this takes when we're all done. Let's make sure that we just get it step by step. We're going to do this partition of each column all the way across. And each one is done completely independently. Each one takes 6 comparisons and then a couple of moves to partition it. Some constant number of moves, because they're all 5 long. So we do this all the way across. Okay. And I'll write step 1. Partition each column. Step 2. Okay, the next step, maybe now I can give you a little idea of where we're going. What we're trying to do here is we're trying to make the problem of finding the kth biggest turn into a problem where we're trying to find the kth biggest in a smaller group of numbers. A group which is ideally half as big as the original group. It won't always turn out to be half as big. In fact, in the worst case, it might turn out to be 3/4 as big. But we're going to get rid of a good fraction of our numbers. And that'll basically give a recurrence equation, basically something like this. Do some work and turn it into a problem which is 3/4 as big. That's our goal.
The 3/4 is going to be constant. You're not going to change it to 5/6 and 7/8.
Well, the number here is actually anywhere in between 1/4 and 3/4. So it depends on what turns out.
Bounded away from what?
Right, and it never gets to 5/6. Right, 3/4 is the worst that it gets. Right, if this becomes t of n minus 1, then we're back to an n squared kind of a thing, and that's no good. So we want to make sure that whatever it is here, that it's some kind of a fraction. N over 2 would be good, but 3/4 of n, it turns out, in the recurrence solution will work just as well. So that's our goal. So how is it going to get that way? We'll write a real recurrence equation up later, just a little forward look. Here's what we're basically going to do. We're going to take this middle row, just the middle row now, and figure out the median, the center value of that row, and partition that row. So now I'm going to put a big star here. This is the middle value of this row. This is done recursively, because this is not a constant number of elements. This is n divided by 5 elements. This is actually has 1/5 of the elements of our whole array, and you need to find the median here recursively. You call it recursively on a list, and you say, give me the middle one. You find the middle one, and then you partition this row just like you do in quicksort. So first find the median, and then partition it left to right on that value just like you do in quicksort. So now this middle row is partitioned with little star minuses on the left and little star pluses on the right. So these are smaller, these are bigger. This is the median of the middle row. And when you do the partition, don't just move the middle row around. Move the column along with it. Otherwise, we have lost the structure that we spent so much time doing at the beginning. So when you move this one to this side, take the whole column and move it together. So I still know that these are smaller than this one, and these two are bigger than this one. I still know that whatever's above here is smaller than this, and whatever's below here is bigger than this. OK, let me stop for a second. Are there questions so far? Let's write that down as step 2. Partition the middle row on the median and move the length 5 columns around appropriately. All right, so 2 steps. First, partition each column, get the medians in the middle. Then take the middle row and partition it into 2 parts, where the middle is here. Move the whole column from left to right as necessary, so that the whole picture still has this nice structure that above is lower elements, below is higher elements, and here's the center of the middle row.
So are the elements in order now, or do we just know that they're less than?
They're not in any particular order. There's some structure in this array, but they're certainly not in order yet. Well, if they were in order, then we would have sorted it, and that.
But every column is in order, and the middle row is.
The columns are not in order. They're just partitioned. These are smaller and these are bigger, but they don't have to necessarily be in order. So let's identify what section of this rectangle have numbers that are definitely smaller than this. And where are they? Smaller. Smaller than this middle guy. North, west, right? I'm going to... Oh, yeah, good. Duh. Right, from here. Smaller than big star. Okay? What are the big ones? The ones that are bigger than it. So it goes, right? Larger than big star. Okay. Now what? What about these guys? Never Never Land people. Never Never Land. You don't know anything about them. They could compare to this arbitrarily. Either one could be larger or smaller. So you know what we do with these? We go through them one by one and decide which set they belong in. Either this one or this one. So that's step 3. Go through each element whose relationship to the big median is unknown, and place it in the correct set. So we have 2 sets, one that has elements that are bigger than this middle one, and one that has elements that are smaller. And as you can see in the picture, even if things completely get lopsided in these 2 unknown areas, what's the most lopsided these 2 sets can be? They can be 3/4 and 1/4. They're never going to be worse than 3/4 and 1/4, because we already have a guaranteed 1/4.
Sure.
what happens if it's not a 5 by, 5 by 5 array, multiple 5 by, let's say you couldn't finish your last column, and then it could be worse than 3/4, right? Let's say and then you shift them all to the smaller then?
I think actually, see these things in the middle that kind of give you more? I think that makes up for the possible.
In any case, it'll be 3/4 plus epsilon.
Right. It won't matter, but I think it actually still is 3/4 because we have these middle ones that are in our favor. And even if you can't finish up the bottom here because it's not a perfect multiple of 5, that will make up for it. Okay. Yeah, Chris?
Is that last one, say you only have 3 values in your last column,
Mm-hmm.
is the thing in the median row element 2 or element 3? The question is,
Oh,
what do you do with the last row in terms of finding the median and positioning it in the array?
If the last row was.
They only have like 1 element or 2 elements or 3 elements?
you mean if there's just blanks down here?
Like let's say there's 26.
The last
Let's say
column.
there's 26
Right.
things you're sorting.
Over here.
Yeah. So if there's 26, your 6th column only has 1 element.
Mhm.
Where does that go? Do you call that the median? Do you call that the thing that goes up in the corner?
Oh,
It'd probably be the median.
yeah. I think, well,
So then you have blank spots.
I think that the answer is I never thought about that, but what I would probably do is fill out the array with dummy values to make it an even 5/5, where they would just be, where you just don't care about them.
In any case, it's a constant. If you fill it into or less than 5, you can just check each of them against the median.
You could, right? There's only whatever, some constant number, and you could just leave them out and check them by hand. But I guess you could do it either way. You could either make it the median or just throw them up on top. And I'm not sure. I have to think about it. I'm not sure what the best way is. It's a good question, but I'm not sure. So let's assume for now that it's actually even, so we don't have that issue. It may be an issue that we should deal with more carefully. Okay. What's next? We got these 2 sets. We did all this work to come up with 2 sets, one of which is bigger than this star and one of which is smaller than this star. How does that help us?
You now reduce the problem to the kth largest in the 3/4 of the original set.
Is it always in the 3/4? Well, let's say, depends. Let's say we had 100 to start with, and the 2 sets split up 32, 68. 68 are larger than some star element, and 32 are, I guess, 31 are smaller. Here's the star element. Okay? And you originally wanted the 45th largest. Okay? You originally wanted the 45th largest. You did all this work, and now you have 2 sets, one of which has 31 elements in it smaller than this value, whatever it is, and one of which has 68 elements in it larger than this value. You wanted the 45th biggest. What do you do now? You want to do something recursive now.
The 13th biggest of 68.
If you look for the 13th biggest, here, why 13th? Because 31, 32, and 13 more give you 45. The 13th biggest in this set will be the 45th biggest in the original set. Does everybody get that? So you figure out which one you were looking for originally, subtract off the number here plus 1, subtract off 32, 45 minus 32 gives you 13, and look for the 13th biggest here. And then you do it recursively from there. Let's say you were looking for the 27th biggest, because that's the other possibility, that it doesn't end up in the right side, but it ends up in the left side. If you're looking for the 27th biggest, that's even easier. What do you do then? You just run it recursively and look for the 27th biggest in the first set without any subtracting off the first 32. Okay, who gets it? That's the most important part of the whole algorithm. All this is preparation just so we can do that. So maybe let me say it one more time and we'll stop for a second for questions. You split it into two parts, which are guaranteed to be no worse than 3/4 and 1/4 of your original 100. You have some value that you've partitioned your elements on. Here you've got at least 3/4, here you've got at most 1/4, or vice versa. And now you ask yourself, well, which one was I looking for? Let's say you were looking for the median. Let's say you were looking for the 50th biggest. That ends up going over half. So you take away these 32, it leaves 18. And you're going to want to get the 18th biggest in the second half. That'll give you the 50th biggest in the original. Okay? Questions so far?
So we just did a cell-by-cell comparison to determine the relation to all of the ones that didn't fit in one group or the other. Is that right?
Right. All these we do a one-by-one check. Right.
Is there any guarantee on what portion that will be?
No. They could all end up in one set or the other. That's why in the worst case, you might get 3/4 versus 1/4. And this is modulo Chris's question of what happens when, maybe this has some empty values in it and they all go in the other one. It could actually maybe get a little worse than 3/4, but I think we're talking about a constant value one way or the other, and it won't matter. So let's just assume it's even. But you do have to go through these one by one, absolutely. Okay, so that's the algorithm. It's a lot of work and then a recursive call. There's also a recursive call in the preparation. Where is that? There's one recursive call in this preparation. Where did that happen? Good. When we got the median of the middle row, that was a recursive call that took this particular array and asked for if there were 20 things in this row, which there would be if we started with 100, it asked for the 10th biggest in that row. So that's another recursive call. There's actually two recursive calls, one the most important one at the very end, which turns it into the subproblem, and one which is just helping us get the preparation done. So now we're going to write a recurrence equation that models the time of this. Now this is an algorithm that you really cannot analyze by looking for the sum and adding it up, because this is really a recursive algorithm that's a mess to analyze if you try to do it iteratively. So you really do need some recurrence equation, and the recurrence equation is really ugly in the sense that it's not easy to just solve it by substitution. So we're going to need some fancy technique to solve it, and we're going to stop at that point. I'm not going to go through the details of solving it, but I will tell you the technique that's used. All right, let's come up with the recurrence equation. That is what I do expect you to be able to do in this class. So let's do it real slow. Make sure everybody gets it. Okay, step number 1, partition each column. How many steps does it take to partition one column? It takes 6 comparisons. And then you have to move them around a little bit. That's some constant number. But it's a constant number. We can call it 6 or call it 8 or call it 9 or 10 depending on what you're counting, but it's certainly a fixed number. And how many times do we do it? N over 5 times. Right? Because there's N over 5 columns here. So the first step is N over 5 times, pick a number here. Is it right to say 6? Is it right to say 8 or 10? Decide what you're counting and pick it. It's constant, and you can call it C0 or C1 if you want to. And then you could have your inductive proof be based on what those constants are. But for now, let's just call it 6 and assume that we get the other stuff for free somehow, that we're just counting the comparisons. It doesn't hurt. Next step, step 2. Partition the middle row on the median and move the length 5 columns around appropriately. So there's 2 parts to this. Finding the median takes a recursive call. What size? Anytime you're doing a recursive call, then in your recurrence equation, you're going to have t of something, because we're doing the problem again. How much time is it going to take us to do this problem again? But now the list is smaller. How much smaller? It's a fifth as big. So this is Tn over 5 plus, how much time does it take to move these things around? Well, partitioning this takes time proportional to its length, right? Remember when we partition in quicksort, it takes time proportional to the array. You have to move the pointers in from the 2 ends until they crash. Every time we swap here, we actually swap 5 elements, right? So let's count how many steps altogether. What do you think? This is n over 5, right? Times some amount of steps to swap the 5 columns. You can call it 5. You can call it, if every swap takes 3 steps, you could call it 15. What do you want to say? 5, 10, 15? It doesn't matter. It's going to end up being a constant. So let's say it costs, what do you want to say it costs for each movement? Worst case. 3? Fine. Keep in mind what that 3 means. It means that's how many steps it takes to move one column to another spot somewhere else and swap it. All right? It's going to be more than that probably in practice, but it's fine. Some constant number. What did I say in my notes? Probably not 3. I said 6?
You said 17.
I said 17. I did? Said 17?
You did. It's right there.
I wonder why. I probably counted 3 for every swap, times 5 is 15, and then 2 more for the maybe moving of the pointers. I picked 17. All right. But we're going with John today. It's the British 3. Step 3. Go through each element whose relationship to star is unknown and place it in the correct set. Yeah, Mike?
Quick question, Chai. How come it wouldn't be n over 10? Because it seems like you wouldn't swap them all twice. You're only going to swap.
Well, you have to move the pointers in from both ends until they crash. So the pointers are going to move n over 5. You might only do n over 10 swaps, but each swap is going to take 15 kind of things. Maybe 17 isn't the best or something, but it's going to be some constant. It's certainly more than n over 5. No, because the partition itself takes time proportional to this whole list. The pointers move in one at a time, and they crash in the middle somewhere, but the total amount of movements those pointers make is still the length of the whole array, and not half of it. So it still takes at least n over 5 times something. Okay. Last step. How many steps does this take? Worst case.
Don't we have to account for the steps to determine what the median is?
That was this. That was this recursive call. So we did.
No, but that's the T n over 5s for the medians in the columns.
No. Those are 6.
Okay.
Right. So this is for the row. All right, last step is these 2 corners that are unknown. And we just have to do these one by one. And how many elements could be in these 2 corners combined together, worst case, is about half, right? So, n over 2. A lot of work. Now they're in these different sets. And we haven't talked about how to implement this. I mean, that's like implementing this is a serious question. I mean, how do you actually run the thing recursively on just the middle row? Do you pull it out into a separate data structure? How do you implement the sets? Do you have different objects for the sets? Do you just do them in place? There's a million questions about how to do this in detail at the bottom level. But we're not dealing with that now. We're just trying to talk about the algorithm on a little higher abstract level. Yeah?
Just a quick question. We're not guaranteed yet that big star is the true median.
Oh, no. It's definitely not the true median. It's not. Almost for sure not. And it can be anywhere from the 1/4 spot all the way up to the 3/4 spot. But the chance of it being in the center is 1 out of whatever that range is. Yeah. That's a good point. This is not the true median, right?
We've done our one recursive call. Don't we need our second recursive call?
Yeah, we're not up to there yet. Yeah. Last step. Last step.
Speaking with finality. I thought you
Oh, no, never. We're not done yet. Right, the last step, which is really step 4, I never wrote it down, is to go ahead and run the problem again on either the first or the second set, depending on where the original number you were looking for lies. If you're looking for the 25th biggest, it lies in the first set. If you're looking for anything past 32, it lies in the second set, and you would subtract 32 off of the number you're looking for and do a recursive call in the second set.
Do you already know? So we have to know how many elements are in the smaller group, right?
Right, and in the larger group.
Side effect of what we've done.
I think while we're going ahead, and I mean, we can just, it's not,
Just another count.
right, it's just keeping a count while we do the other stuff. So it will add a constant factor, perhaps, of 1 extra step to this, and to this, and to this. But it doesn't affect any overall analysis that we've done so far. But we definitely need to keep that count, that's true. Or in fact, what we could do is just not keep it, and at this point, count up the two sets. We could do that too. Probably if you really implemented this, your set would have some kind of a method, that says get size of the set, and you would use that right now, and who knows how that's implemented. All right, how much is the last step, worst case? Right. T of 3/4 n. The idea is that the worst thing that could possibly have happened is that all these unknowns went into one of these, making it 3/4 of the whole space, and you'd have to run your algorithm on that whole space. Okay, which is more or less what happened here. I mean, 25, 75 would have been the worst, and say you have to look in the 75 set. So that'd be the worst case. So here's the recurrence equation. Yes?
These recursive calls take the data set and the number that you want looking for.
Absolutely. Right. They take an array and they take a k. And the k can start off perhaps as the median, but then the subsequent recursive calls might actually be looking for other kth largest based on how lopsided it got. Right. That's an important thing, that this is a recursive algorithm that really finds the kth largest. It can be used to find the median as a special case. All right, one thing you can do with this, if you want to torture yourselves a little bit, which I know you don't, is you go home and you try to solve this by substitution. Okay, you write down Tn over 5, T3n over 4, you see what they equal, you substitute them back here, and you keep going down, 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 and you get this long thing, and you hope to God you'll be able to look for some pattern and formula and see where it's heading, and you might be able to do it. In fact, you can do that. It's just a little ugly mathematically. The other way, and this is a technique that does work very easily, and it's usually the one most textbooks use because it requires the least pain, and that is to say, well, look, we're trying to make this linear time. We think we've made it linear time. How come? Because we've got fractional pieces here, that this looks more or less like something like this. It looks more or less like t of n equal t of a fraction plus some linear time amount. Right? That's basically what we've done. And hopefully that's going to end up be linear time. You have to be a little careful because let's look at this for a second. Here's a very simple version of a recurrence equation like this. What's the solution to this? Anybody know? You get n the first time, and then it's half as big. You get n over 2 the next time, and n over 4 the next time, and n over 8 the next time, right? So have another fraction of n, Zeno. It's half, 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 half. N plus all those fractions end up being 2n. Okay, that's like Zeno's paradox going halfway. So anything that looks like this is going to be okay. Anything that looks like this is not going to be okay. What does this turn out to be? That turns out to be n log n. That's the recursion for quicksort. That's the recursion for merge sort. So we want to make sure that what we get here is more like the top than like the bottom. Now it's actually kind of like a hybrid, right? I mean, we've got this T3n over 4 and we have this Tn over 5. So it turns out that if you do the analysis, it ends up being more like this and not like this one. And you know what the key thing is? The key thing is that this 3/4 and 1/5 is less than 1. Because if this really were a quarter, then it wouldn't end up like this. It would end up more like that. So that's the whole trick here. Why do you pick 5? Why do you do it in this weird way? It's just this nice relationship between the 3/4 and the 1/5, that when you add them together, they're smaller than 1. All right? So if we had 4 here, 4 rows or 3 rows, it wouldn't work, right?
So why wouldn't you take a large number like 7?
Maybe it would. This is the smallest number of rows that it could work with. You could use 7. But then there'd be more constant factors in doing the step. It's a trade-off and an engineering question, really. But certainly, the smallest number of rows that this idea will work for is 5. It's not going to work for smaller than 5 because the recurrence equation won't turn out to be like this one. It'll end up turning out to be like this one. All right, so the way you actually solve this recurrence equation is you don't solve it. You guess that it's smaller than or equal to some constant times n, and then you convince yourself that that's true by induction. right? And Mark can do that in recitation. We've actually done this in discrete math. We've done something just like it. Assume by induction that this is less than, say, 192n. Okay, and then use that inductive assumption to substitute this with something smaller than 192n over 5. Substitute this with something smaller than 192.3n over 4. Add these together and hope that you get something less than 192n, and that proves your assumption. And if you don't remember that, or that seems too fast, then you'll see it again. Mark will do it again. All right, but that's the way we normally do it. Guess the solution, prove it's true by induction. So this is linear time, and the reason intuitively I told you before is that those two add up to less than n, and there's our linear time algorithm for kth largest. I know about strange, yeah. What I want to say about strange is again, the trade-off between talking about some theoretical idea like this and proving that it's linear time and actually going ahead and doing it and seeing what works in real cases. You got to have this instinct that actually doing this would be a pain in the neck. Right? I mean, actually getting this program to run look, it only took me a half an hour to describe it to you. And I think everybody probably pretty much gets the idea. But if I had to go right now to my desk and sit down and make this work, it would take me a good deal of time, probably well into the afternoon, before I really got all the bugs worked out and got all the data structures worked out the way I wanted. There's a big leap between making something work and just thinking about it. So what I want to talk about is something that shows up in your problem set a lot, and there's a moral here that I want you to absorb. It's not related to this algorithm, but it's related to the idea of the relationship between theory and practice. This is the amount of time it takes to find the kth largest if you use the heap sort idea. N time to build the heap, the fast way, and then log n time, k times over and over again to find the next biggest and the next biggest until you do it k times. That's the straightforward way. It's really pretty straightforward. You build a heap, the algorithm's right in the book, and you go ahead and fix your heap k times, putting the next biggest one on the bottom until you're all ready. Now, you can actually write this. This wouldn't take well into the afternoon. This would take you about maybe half an hour to an hour if you're a good programmer to get this thing done and running. And it runs pretty fast. I mean, think of how fast it runs. It's just n time to build it and then k log n. It's pretty quick. If you're looking for the fourth biggest, it's n plus 4 log n. Now, in the problem set, I ask you to think really, really hard about a very, very clever idea that will actually take this method and knock it down to n plus k log k. The idea here is that somehow you're going to do this method so that your heap, instead of modifying a heap that has all the elements in it, you're modifying a heap that has at most k elements in it, where k is the biggest that you're looking for. Now, let's not get into how to solve it. I'll be happy to tell any of you how to solve it if you've thought about it for a while and you get to a brick wall. I mean, it's actually, you'll probably figure it out yourself if you think long enough. It's a clever solution. But whatever the solution is, it does knock this n down to k. But let me tell you this. The solution does involve using a second heap. It does involve using kind of a reverse index. If somebody gives you the value, figuring out where it is in the original heap. It involves a lot of constant overhead. So Mike Sisolak's not here, so I can talk about him. I sat with him the other day, and he was working on this problem, and he's a very quick and fast programmer. He wrote this up very quickly, and then spent a lot of time after I went through the solution with him writing this up. And we tested it. So which do you think took more time? Well, it's a loaded question. Right? This one ended up taking more time for the first 8 or 9 tests that we did. Well, what does that mean? It's really weird, right? This is supposed to take less time. Well, let's think. How much less time would you expect this to take? I mean, the n's are exactly the same. The k's are exactly the same. It's the difference between log n and log k. Let's say k was n over 2 for a minute. What's the difference between log n and log n over 2? Log n over 2 is log n minus log 2. The difference is 1. So the difference here, even for very big n, is very small. And the constant factors, let's say the constant factor here is 10,000 and the constant factor here is 32. You're going to have to use some pretty darn big n to start seeing differences there. You'd have to use an n, well, so you'd have to use a k that's at least 32,000. Because the difference between log n and log k is only 1. So the difference between these two would be 1 times that 32,000. You're not going to see a difference in the two algorithms until you get to some really huge k and some huge n. So I suggested that to him. But once you get to a very, very big value, Java starts coughing up blood and goes to the hard drive, and then measuring how much time it takes becomes ludicrous because the system overhead has become dominant. So we went down to lower cases, and finally, with me suggesting a good set of data that I think would really show the advantages of this, we finally tried it, and it did show that this ended up being about twice as fast, up until a certain point. So I'll give you the exact numbers we used. We used n equals, who was standing next to me? Who remembers these numbers? N equals 50,000, was it? And k equals 100, something like this. This worked out in favor of this. That was all right. And then if we tried 150, it flipped. So we did a little binary search to see at what point it flipped. It turned out that 134, it did what we thought it would do. This was faster. And at k equal 135, one value more, this became much, much faster than this. Well, what's going on? This is a very interesting question, and I think actually we don't really know what's going on, but there could be some nice research done into just this kind of stuff, which is much more experimental and engineering oriented than most people would think of algorithms as a topic. But there has been in the last 10 years a big move to thinking of algorithms both as a theoretical subject and as an experimental subject. And here there's a lot of issues. One, did Sisolak goof up in his algorithm? Maybe he did something weird. I checked it and he didn't, so that wasn't the issue. What do you think the issue is? I'll tell you what my guess was after you make some guesses. What do you think's going on here when it freaks out so badly between 134 and 135 and consistently, every single time the same way? I really don't know what's happening, but I have a guess. Does anybody have an idea what they think's happening?
Consistently every single time the same way.
You run it again for the 134 case, and this one's faster. You run it for the 135 case, and this one's faster.
But always with the number 50,000.
No, you could change that a little bit, actually.
And how did you select it?
Yeah, right. It's really the 134, 135. At least that was our experiments.
The other, since you're having to build a new heap for this, you might be running into memory issues or something, and you need to...
Yeah, but the new heap is smaller than the first heap. I'll tell you one thing. I mean, the truth is, it's just in the dark guessing unless you actually see his code. But I'll tell you one thing is that fixing this heap is in a loop that doesn't create new objects every time through the loop. It just manipulates this one heap object that stays the same, and it manipulates it and doesn't have lots of overhead and probably not a lot of extra memory getting dynamically allocated. But doing this, the way he implemented, because Java enforces this nice structure on the program, he was forced in doing this implementation to create new objects all the time in the second heap because he had to have references back. Forget the details, you won't get it unless you actually see the code. But the way he implemented this, there were lots of objects being created. So my guess is what happened is that Java does garbage collection at a particular point, and the size of whatever structures he's using triggers a garbage collection to kick in right after 134. That's my best guess, because otherwise the results are really hard to explain. But again, it's a guess, and you really need to look and see what's going on and see if it is doing garbage collection then and see what's happening.
Why would the garbage collection cause that sort of...
Because the garbage collection takes a long time, and there's no way to cut the timing out of the... He ends up timing the garbage collection, which isn't timing the actual algorithm itself. So the moral of this is that there's a lot of interesting questions to ask once you're past the theory. And this looks like it's an improvement, and if you came up with this improvement, you could publish it, and everyone would say, very nice improvement. And the question of whether it's a practical improvement or not is left to the engineers, and the engineers have to be smart enough to understand what this is talking about, and also smart enough to say, very nice, go back to your theoretical work, or very nice, I can really leverage this into something that works. And that communication has to stay strong. The minute the theoreticians do not address those issues carefully, and the minute the engineers are so far removed from what they're doing that there's no communication, then the whole field really breaks down. And this is especially true in computer science. Computer science, the math is motivated by the practical issues. and not just by what seems beautiful. Sometimes it's by what seems beautiful, but there's got to be a good reason that you can give at the bottom line that makes things work. That's the difference between a theoretical computer scientist and just a pure mathematician. All right, enough of this. Let's talk about searching and a data structure called binary search trees. This is going to lead us into red-black trees. We talked about a data structure called a heap. And a heap was a great way to let us insert items and delete items and change items and pick out the largest one among those items. So it was a good way of implementing a data structure that you've seen before called a priority queue. Like a line at a bakery is my typical analogy. There are other ways of implementing priority queues. Some ways are really inefficient. If you just kept all the elements in a straight array and didn't even keep it sorted, then you could find the biggest one, but that would take order n time to find it. But adding would just take constant time. You just throw it on the end. So inserting and searching would have this very unbalanced position. Search would be order n. And what I mean by search is give me the biggest one. And inserting would be order constant time. That's if it was an unsorted array. A sorted array would have exactly the opposite situation. A sorted array would give you the biggest one in constant time by just pulling out the front. And the inserting would have to be done by finding the appropriate place and putting it inside and then shifting everything down. So that would take worst case linear time, because you'd have to shift everything down and make room for the spot that you had. So it would look like this in a sorted array. Order 1, order n. In a heap, both these numbers, both these searching and inserting is done, well, the find is done in constant time, but inserting is done in log n. When you find it, you might have to fix the heap. So finding it is order 1, but fixing the heap is really an extra log n. So it's really, order 1 is a little fishy. That's just to find the value. But to keep it a heap so that you can do another find afterwards, you have to fix it and it takes order log n. So using a heap balances this data structure so that the operations, instead of being constant and linear, are both order log n.
You say we have to fix the heap. Are you assuming we're removing the element that we searched for?
Yes. If you're just looking for it, it's fine. But if you're going to remove it, you have to fix it. Yes, that's right. So if you're just looking for it, it really is order 1. But typically, you'll remove it, and then you have to fix the heap, and it's order log n. So I don't want to think of this as order 1, because it's kind of cheating, because very often you remove it. Good. All right. There are other ways of doing exactly this kind of data structure. This kind of data structure is, and associated operations is sometimes called a dictionary, because you can pull things out from the beginning, you can find things you're looking for, you can insert things, you can delete things. And heaps are one good way. It's the first way you've seen. And now we're going to talk about binary search trees, which is another good way. But binary search trees let you do a little bit more than heaps. They can also implement priority queues, but they also let you search for things and find things very, very, very fast. Not just the biggest thing, but anything you're looking for. So they're a little more general than heaps. And they have the application of both priority queues and sorting and searching. You'll see these in a minute. So what's a binary search tree? It's kind of straightforward. Before I write it down, let's just review binary search really fast, make sure everybody knows what it is. Binary search is a way of looking for something that finds it in log n time, where n is the number of things you're looking for, or the number of things in which you're looking for. So if you just have an array and it's unsorted and you're looking for something, the best you can do is just look for it. That's like a tape with just a random list of songs on it. You're looking for the song you want. You got to fast forward through the tape until you find it. And the worst case is you got to actually go through the whole tape to find what you're looking for. But if it's ordered, and you can go ahead from one spot to another on your tape and have the intervals, you can do a binary search. So that's like a game that kids play. I'm thinking of a number between 1 and 32. So the kid guesses 16, and if it's too high, then the kid guesses 8. And if that's too low, then the kid guesses 12, and you narrow it down. Every time you make a new guess, you have the interval. So it takes log n. Binary search is very fast. We'd like to do binary search and not linear search if possible. So a binary search tree is a way of storing information so that you can retrieve it using binary search. And here's the idea. Let's say we're just storing numbers to make things easy. At the top of the tree might be the number 8. Then on the left branch of the tree will be numbers that are smaller than 8. And on the right branch of the tree will be numbers that are bigger than 8. Okay, so here might be a number 7. Here we might have a 5. Here we might have a, uh-oh, didn't leave enough room. Yeah, okay, good. 7.5. This will be 15, 12, 18. This is a binary search tree. At every node, all the children to the left are smaller than this, and all the children to the right are bigger. And that goes recursively down the tree. All the children to the left of this are smaller, all the children to the right are bigger, etc. All right. So let's say I'm looking for the number 12. It doesn't have to be numbers. These could be records of information. I might be looking for, all the stuff associated with Shai Simonson. So I'm looking for that. That's my index. I compare it with 8. And I ask myself, is it 8? If it is, I'm done. If it's not 8, I say, is it bigger or smaller? If it's smaller, then I recursively start at this subtree. And if it's bigger, then I recursively do the search on this subtree. So every time I'm through, I cut my problem in half, seemingly. And I finally work my way down until I find the 12 I'm looking for. OK? You're all familiar with this? Is this review or is this new? Review, right? Kind of? You don't want to say. What's coming next? All right. How do you insert into a binary search tree? I got a new value. Mr. 17's coming in. Who's got an idea? How do I put him in?
17 is larger than 8, so you go down the right branch.
OK, you do like you do a search. 17's bigger than 8, so I go here. 17's bigger than 15, so I go here. 17's smaller than 18, so I go here. And it goes right there. OK?
Like our tree could get unbalanced.
Good. That's an excellent point. That's an excellent point. Let's say I want to add in 20. Where does that go? Bigger, bigger, bigger. And now I'm going to add in 25. Where does that go? And then 30. And 35. And 40. And right down into the Kendall Square subway station, 50, 60, 70, 1,000 more. Boom, down it goes. This tree has lost its bushiness and its robustness and its evenness, and it has now become one long, stringy, scrawny tree. Well, why is that bad? Why do you care if it gets unbalanced?
Search for 995, you just have to go all the way down that way.
Yeah, if you try to search now for, say, 995, which is down in the basement, it's not binary search anymore, where every question splits it into 2 equal parts. It is for the first 3 steps, but after that, every single question just rules out one element. It becomes linear. It's just as if I stored these things in a long line. So binary search trees are great in theory, but they are really bad unless you can guarantee that that search tree stays balanced to some extent. And let me tell you right off the bat, forcing the search tree to stay completely balanced like a heap is virtually impossible. So there is a trade-off here. We have to keep it balanced to some extent where we still get this nice performance, but allow some flexibility of variation so that we can at least manage the balancing. There are many ways to do that. A very early method is called AVL trees. These are no longer taught because Red-black trees are better than them, have a little better complexity. So the red-black trees have taken over AVL trees. And alternatives to this are B trees, which are used mainly for database storage. As you can imagine, this is perfect for database, this idea of a binary search tree. B trees are used for databases. And other variations are weight balance trees. These two possibilities are called height balance trees. The difference between these two, very obvious. Height balance means that the distance from the root on the left side is very similar, if not the same, to the distance from the root on the right side. That they're height balanced, that you don't get any long stringy things. Weight balance means I don't care how long the paths are, but the number of nodes on this side is going to be very similar, say within 90% of the number of nodes on the other side. Height balance trees are much more popular, easier to deal with. And there's plenty of papers on weight balance trees, but they are not the general way of handling this.
When you talk about height balance versus weight balance, are you generally only talking about from the top node, or do you?
No, from each node. No, recursively down through each node. Each node has to be balanced, and then including the top node. Yeah, absolutely. Otherwise, you would only know that you have the good performance on the first question, and then afterwards, you wouldn't necessarily have that.
Shai, are we going to get into more detail later on red-black trees? I mean, not necessarily today, but...
Yeah, necessarily today. Well, today or tomorrow. We're right there. I want to talk a little bit more about binary search trees before we go on. This may or may not be a review, but bear with me if it is. How do you store and implement a binary search tree? You need to create a tree, and every node in your tree needs to have a left pointer and a right pointer. You can also add other things in your tree. You can have parent pointers that go back. Some trees, you only have parent pointers. When we do shortest path algorithm and minimum spanning tree algorithm, our trees are going to be defined strictly through parent pointers, and we implement it using an array. Nice and easy. But when you have a tree that have left and right pointers, then you really need some kind of dynamic structure. And you'll see this in recitations exactly how you implement it. But keep in mind that from a node, you have a left feature, you have a right feature, and you can move to other nodes, which are recursively also have left features and right features. Now, just with that, so we have a pointer coming into the top that's called the root. And that's what defines the tree. Root points to here. Each node has a left and right. How do we do anything with this tree? How do we search it? Searching it is easy. Check root.data to see if it's what you're looking for, and if it is, you're done. If it's not, compare your value to root left data. Compare your value to root.data. If it's smaller, go to root.left. If it's bigger, go to root.right. So you're going to move left or right depending. The normal binary search operations are fine if you have left and right. What if I wanted to print out all the nodes in my tree in some kind of reasonable order? Let's say sorted order. How could I do that? How could I go through my tree and print them out in sorted order? Here's a way that doesn't do it in sorted order. I print them out a level at a time. 8, 7, 15, 5, 7.5, 12, 18. That's just the level order. That was really useful for heaps, but completely meaningless here. You could do that using a queue. You could put the root on the queue, delete it from the queue, look at its children, put those on the queue. Keep deleting from the queue. 15 comes out next. Put its children in the back of the queue. A queue is a nice way to get a level ordering of a binary tree. But it doesn't help here. So the heck with queues, and we need a better way to print this tree out. Well, the way to do it is using recursion. And it's a very natural way. What do you know about this tree? All the values smaller than 8 are on the left side. All the values bigger than 8 are on the right side. So if you want to print out all these values in sorted order, all you have to do is first print out this subtree recursively, then print out the root, then print out the right subtree recursively. And that's called an in-order traversal. In order means first left subtree, then root, then right subtree. Recursion, left subtree, then the root, then recursion, right subtree. So an in-order traversal of a binary tree is a sorted listing of all the nodes if the binary tree is a binary search tree. Are there questions about that? Okay, so first you recursively go to the left. In order to do this, you recursively go to the left. This is the first one. This is the second one. This is the third one. Now you're done with this, so you do the root, the fourth one. Now you do the recursion on the right. In order to do this tree, you go left, you do the root, and then you go to the right. Everybody, you guys can run through this recursively? Okay. So an in-order traversal is good for sorting. There's also, once we're mentioning in-order traversals, something called pre-order and post-order. And there's a lot of nice uses for these. They're used a lot in compilers and in getting in calculating expression trees, as they're sometimes called. But I won't get into applications now. Let me just get into what they are. Pre-order means that you first do the root, and then you do the children. So what's the order that it would print these out? Let's try to do it. First do the root. That would be 8. Then the left subtree. 7. Then the children. 5, 7.5. Where are we up to? We did the root, the left subtree. Now we're going to do the right subtree. Root, left subtree, right subtree. So 15, 12, and then this one is 18, 17, and 20. That's a listing of these in pre-order. And post-order does the subtrees first, and then the root. First you do these two, and then you do this. Which is the first node printed in a post-order of this? Left, then right, then root. So how do you do this one? Left, then right, then root. So 5 would be the first one. And there's some really nice applications of it, but I'm not going to get into them right now. It's a good question. It's a really good question. Okay, questions so far? Other questions?
This. Post order. When you're going down the right side, you get 12.
In post order.
Yeah.
So the first, let's do the post order.
Yeah,
the post order means we're going to first do the left subtree, and then the right tree, and then the root. So the last thing is going to be the root.
Right.
Left, right, root. So 5, 7, 5, 7, and now the right subtree of the original. Left, and then right, left, and then right. So it's 17, 20, 12, 17, 20, 18, 15, 8. That's the post-order traversal of this. Okay?
That's what I thought.
Okay.
I wasn't sure.
Yeah, no, it's fine. This takes a little practice, but I think, you know, the reason I'm not spending a lot of time in this is because I think this is just the stuff that I expect you to be good at after surviving through the scheme course. And you may not be good at it yet, but I'll be happy to work with people one-on-one and make sure you're good at this. All right, so here's where we have a little more time today. Here's where I'm headed. I want to explain how to make these binary search trees robust, to keep them balanced. And the method that we're going to talk about is the red-black tree method. All right. Now here's the thing. I'm going to try to motivate red-black trees so that they make some sense to you. But at the beginning, they are going to seem a little arbitrary. But I will try really hard to at least convince you that intuitively there's a reason for the seemingly arbitrary definitions. And the reason is to keep this tree kind of balanced. I'm not going to get into the proofs of any of the math, but I'm going to tell you what these definitions will imply about the balance. And here it goes. A red-black tree is a binary search tree with a bunch of very specific properties. And here they are. Every node is colored red or black. Done. Let's go in order of the easiest ones. All leaves. That means all the nodes at the bottom, and you should understand what this means because it's a very annoying definition and it's easy to miss. This actually means the nils at the bottom. It means the things that point to nothing, the actual nothings, the bottom, the nils, those are all black. So if you actually draw a tree, you can have reds that look like they're at the bottom, but the nils that they point to are considered black. All right, so all the nils, all the bottom, all the nulls at the bottom are black. All the leaves, meaning the nils, are black. So that even the null pointers at the bottom have colors and they're black. All right. Up until now, there's nothing about a red-black tree that would make it bushy. It could be just as skinny as any other tree. You just color the nodes. It's like I give the tree to my kids and I go, here's a red and black crayon, color to your heart's content, but make sure the bottom is all black. They could do that and it could still look nice and scrawny. All right, so there's got to be more to it. Here's another rule, and here's where my kids would mess up and make a mistake. Every red node has black children. So anytime you color a node red, the children have to be black. Yes. Yes. But if you have a black node, you can have any color children you want. Okay? We're going to do a little example in a second and see if we can, well, let's see if we can come up with a red-black tree so far, because the last condition is going to nail us down a little firmer. All right, here.
Do these nodes also have numbers associated with them, or are they just colors?
They have other data associated with them, but this is just one more piece of data on top of whatever you're normally storing. So this is colors on top of the indices or data or anything else that you're storing. Is this a red-black tree? According to what we have so far?
No.
Yes. You have to.
The red needs.
Yes. The red has two null points that are black.
Right. Anything that's not listed are null points. So as long as those null points are black, we're OK. It's OK to have the red here. Just keep in mind that the null points that it points to are black. Okay? If this were a red, it would still be a red-black tree. If this were red, it would not be a red-black tree. Right? But this is not enough. I could clearly make this scrawny and skinny without violating the conditions, right? What do I have to do? Just go black, right? I mean, I'm not there yet. But here's the fourth condition, and this is really what nails it. From any node, the number of black nodes on any path to the leaves is the same. That is really bad English and bad wording, so let me say what I mean. What I mean is, if you pick any node you want, and you start from there and you work your way down to the bottom, you will pass through the same number of black nodes. Okay? Doesn't matter whether you go this way, or whether you go this way, or whether you go that way, you'll pass through the same number of black nodes. Or is that true here? Start from here. 1, 2, 3, 3 nodes. 1, 2, 3, 3 black nodes. 1.
Wait a minute. Isn't that 4?
Oh yeah, 4 including the leaves. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. That's not okay. That's not a red-black tree. Brian, you had a question? No? Okay, go ahead. Tony? Yeah.
Actually, does that mean that red nodes happen in layers?
It means you can't go too long without a red node.
every red node's immediate children? Or
Yes.
yes?
Yes. Children mean just children, not
Right.
not descendants. Right. Not grandchildren, not great-grandchildren. All right, so let's turn this into a real red-black tree. How can I fix it?
Add some black nodes on the left, or
Add some black nodes on this side? Is it okay now? Still not, right?
you'd need another generation, maybe of black.
So just change the black next to the red to the red. On the second row, make it two reds.
Make this red? Well, that certainly seems okay, right? That's definitely okay. From this point, you go through the same number of black nodes. This is true from any node, though. What about from here? Do you go through the same number of black nodes no matter how you go down? Yeah. Well, it's completely symmetrical, so you're going to be okay. But it's not so easy to come up with a red-black tree. There are a lot of constraints here. What do these constraints guarantee? What do you think? They guarantee some kind of balance condition. They don't enforce a perfect balance like a heap because it's too hard to maintain a perfect balance. But this is a nice compromise between able to maintain these properties without too much extra effort, and you'll see it's still a lot of effort, but without too much extra effort, and still being able to guarantee some kind of balance. Okay, if I kept this tree completely balanced, then what would the height be if I had n nodes? If it was perfectly balanced? Log n. With a floor or something, right? A ceiling. If I have a red-black tree, doesn't matter how it's constructed, as long as it abides by these properties, then the height of the red-black tree is at most twice this. Okay, it's at most 2 log n, which means it's order log n, which means all the operations that depend on the height of the tree stay log n and never get linear. But it's not at all balanced as perfectly as possible. It can be twice as much off as the ideal. Okay? That theorem that I just mentioned, that if you have a red-black tree, that the height is never more than twice log n, is the key theorem that makes red-black trees work. And there's a long proof of it in the book, and you can read it. And the proof is by induction, as you might have guessed. It's natural it's by induction because it has to do with heights, and if you can prove the heights of the children work, then you can prove the heights of the root work. And it's not an easy, simple proof that I want to do right now, but it's certainly something understandable. But we'll leave it open for now. Yeah, Teresa.
What's the relationship between black and nil? I'm confused in terms of...
Oh, so if I wrote the nils in here, let me write the nils in.
Nils are not black.
No, nils are usually the ones that you don't show, because every node has a left and right child, and these point to real nodes, but the ones in the bottom, the leaves, don't point anywhere.
So a leaf cannot be nil.
A leaf is nil.
But it doesn't have a color.
It has a black color.
Does it have any
So what are
data?
those things hanging off?
These are nils. This is nil, 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 and nil.
Bottom row.
Leaves are not nil.
Well, our text defines the nils to be the leaves here, and they say it's a definition issue. You want to call these the leaves, that's fine. Then the ultimate bottom level is always black. The nils at the bottom are black.
I guess I'm confused because I don't know what the purpose of it is. So
Oh, the purpose of having these nils is that when you're doing a binary search, you have to know when to end. So the way you stop your while loop or your recursion is whether the left subtree is nil. If it's nil, then you don't go down that subtree. If it's the right one's nil, you don't go down that subtree. So nils are used to stop you from going into an infinite loop.
okay, and red and black I used to.
Red and black is our own perception of how to keep this thing balanced. So we're going to have the reds and black values stored in these nodes, and anytime somebody does an insertion or a deletion which might mess up our red-black property, we have to fix it and recolor it.
Oh, so it's a way of keeping track of balance.
Right. It's a way of keeping track of balance and ensuring balance. Exactly. Exactly.
Was it red nodes can only have black children, but black nodes can have either?
Black nodes can have either. Red nodes can only have black children. That's right.
So when you're counting, when you say it can only pass through so many black nodes till it reaches a leaf, does that count the black nil, or? I guess it doesn't matter as long as
It doesn't matter because every single path has exactly one leaf at the end of it.
so it means mostly nothing to say that all of the leaves are black.
Can we just say that leaves can be either color and leave it at that? 'Cause it's not
That is fine. You can change this rule number 2 to leaves can be any color you want them to. Okay?
It's hardly a stipulation at all, hardly a restriction at all, really.
Yeah.
No, black. You adding one.
Well, no, because it contradicts it contradicts 3. See, every red node has to have black children. So if you have a red node and it doesn't have black children, you have to say, oh, the nil. It's number 2 is to avoid having number 3 down and having somebody as clever as you say, well, what are the colors of the nils? And I'd have to say, well, I guess they're really black. And then it's a matter of being mathematically precise. That's really what it is.
Leaves can't be any color at all. 2 siblings have to be the same color.
No, 2 siblings don't have to be the same color.
We just say leaves have.
They don't have to. Here, let's make a red-black tree where 2 siblings are not the same color.
All this does is ensure that we have a balanced tree, and that's it. That's the
Relatively balanced, right. 2 log n as far as the height goes. It's not completely balanced. You can get a little unbalanced.
Show me a sibling that's red and a sibling that's black.
parent is what
I have more black on one side.
All right.
When you say relatively balanced, do you mean within one of the height, or do you mean a complete tree?
It's not a complete tree. It means that if you have n nodes, the height is going to be at most 2 times log n, 2 times the best. 2 times the height of a complete tree.
So kind of balanced.
Kind of balanced, that's right. Balanced to the point of view that we're happy because our height complexities are still order log n. Here's an example from your book. 11, 2, 1. I'm going to have you guys color this as an exercise. 7, 5, 8, 14, 15. Here's a binary search tree.
And you're claiming that 5 can be red and 8 can be black. And I'm claiming it can't be.
No, I'm claiming that this could be red and this could be black. I'll shade the ones that are black, and we'll leave the other ones unshaded to be red. How can I color the rest of this tree and abide by these conditions? This side's black, and this is red, and this is red. If this is red, then these 2 have to be black.
Well, is there any reason why we should color anything red? Because if everything's black, then it always fits our.
It doesn't.
I mean, what is the rule that means we should color anything red? Because if everything is black, we fit all of our rules.
No, it
But
would have to
then-
be a
but
really
then the-
balanced tree then.
Because we.
But
Because
then,
it's only.
right, the number of black, down the right path will have 2 blacks, and down the.
If you colored everything black, then you'd always have to have a complete binary tree. And that's too hard to maintain. So adding in the red actually gives us flexibility rather than takes it away. It lets us make things a little more unbalanced, but still keeps it within a double factor. Is this a red-black tree? The answer is yes.
So what about on the right side, where you have the 14, then go to 15,
Yeah. So from this point, this is black.
and then
It can go down this way, which gets 1 black to its nil, or it goes down this way, which gets 1 black to its nil. This one goes through 1, 2. This one goes through, whoops, 1, 2, 3. This one goes through 1, 2, 3, 1, 2, 3. So this is a red-black tree. The heights work out, but the cousins are not necessarily the same color. I don't know if that's exactly what you're asking, but
I was worried about the leaves. 5 and 8 are leaves, and because they're siblings, they have to be the same color.
They're not leaves.
5 and 8 are.
well, let's call 5 and 8 leaves. Do they?
Why are they not leaves? I'm
Because
sorry.
we've changed their notes.
I'm using the old definition of leaves. 5 and 8.
But here's a leaf and here's a leaf, and they're not the same color.
That's right, but 5 and 8 are siblings.
Oh, you mean sibling leaves? Do they have to be the same color? Let me think about it. Maybe. I bet they do. But. All right. Getting a little more comfortable with red-black trees? All right. Let's rip this red-black tree to shred. I'm going to stop today before the hard part. We'll do the hard part tomorrow, but give me just another 5 minutes to give you a little more intuition about this. What we need to do with red-black trees is use them as binary search trees, but not lose their red-black property. What do you do with binary search trees? Just search for things. Well, searching for things isn't going to touch the red-black property. I find it, I return the data, I don't find it, I mean, that's no big deal. What changes the red-black property in potential is inserting a new element or deleting an element. Let's say I decide to insert the number 4.
Sorry, the slashes mean black or red?
Black. Slashes are black. What color do I make 4?
You have to make it black by definition, right?
If I make it black, what gets messed up?
7.
But you're screwed because you have to have, by definition, every red node is black children. So you have to make it black.
I have to make it black. If I make it black by that rule number 3,
7 is unbalanced.
then 11's unbalanced too, for that matter.
Let's make 5 black as well.
So adding a new node is big trouble. Here's what we normally do. We normally try to go ahead and keep the distance part okay and deal with the contradiction of a red having a red child. So we'd actually make this red because that at least keeps the distance okay, right? It doesn't hurt to add a red one as far as the distance goes. So we make it red, but now we sit back and we look at it and we say, oh gee, I got a red having a red child, throw that red guy in jail. We have to fix this.
By distance, you mean the number of black steps down?
Yes, you're right. The number of black steps still stays the same if we make this red. So this is a very seemingly complex process. There are a lot of things that go on to fix it. Sometimes we recolor. Sometimes we do what's called a rotation. I'll talk about rotations next time. We actually mutate the tree a little bit. We move things around. The worst case in fixing this red-red clash is that we fix it here, and it makes a new red-red clash 1 level up. We fix that, it makes a new red-red clash 1 level up, and we have to fix things all the way up to the top. And that takes at worst order log n. So fixing the tree will take at most order log n to get it back to its red-black status.
Can't changing the root mean you have to leave you with problems on the right subtree then?
It can, but we'll take it. No, we're going to make sure that never happens. We're going to make sure the root always ends up being black, and it'll work out.
You're just not recoloring, you're going to rearrange some stuff.
If we get lucky, we just have to recolor, but almost. You want to know some more details? Here's the details. Jeez. You see these two guys? Here, you got this red-red clash.
Yeah.
This is the kid of this one. These two are red. If this is black, it's harder. And if this is red, it's easier. All right, so if this is black, we have to do rotations and mutations. If this is red, we just can do it easy. Well, here, it's red now. How do we fix this? Because it's not so tough. Here's what we do. Change this to red, and change these two to black. What just happened? You just took this black and shifted it down duplicate. So none of the distances have changed. None of the black distances have changed. But all the reds now have black children, and this guy doesn't have a red parent anymore. You changed his daddy, and you changed his granddaddy. Oh, now we got this problem, red, red.
But it's not going to do any good just to change the colors.
It does right here. We're fixed with this part.
You did have the same tree.
What if this was black? We'd be okay.
I don't know, we don't even need the colors if you're just going to recolor.
As long as we can recolor them according to these criterion, we'll be okay. But Neil, right now we have this red-red that just got shifted up, and we'll have to do it again. And actually, in this situation, it's bad, because in this situation, look at the cousin. The cousin's black here. That's trouble, because now you can't do that trick we did before. I need more time to do this carefully. This is for a separate day. But one last thing before you go. We haven't talked about deleting from a binary search tree. We talked about inserting. Deleting from a binary search tree is a good deal trickier. And I want to talk about that before we talk about doing anything with a black-red tree. Because inserting into black-red tree will take me a half hour to 45 minutes to explain. Deleting from a black-red tree is so hairy that I want to first make sure that we have time to talk about it without the red-black conditions. And then I'll leave the rest of that for afterwards. All right, so let's quit today. Tomorrow we'll go back to deleting binary search trees and red-black tree additions and deletions.